Hi everyone, my name is Megan Flynn and I will be covering Chapter 2 from our Openstax Biology 2E textbook. Again, for those of you that have not accessed your free textbook, you can do so using that link below at openstax.org and clicking on the textbook Biology 2E. So we're going to continue learning through our textbook, Chapter 2. So Chapter 2, we're going to get into the chemical foundation of life. So as always, if you are using these videos as learning points, please click the subscribe button so that you don't miss any new videos posted. So let's go ahead and get started. So in this chapter, we're going to be focusing in on the smallest unit of our biological hierarchy of life, which we learned last week or last video, Chapter 1. So in Chapter 1, we learned about atoms make up molecules, molecules make up macromolecules, macromolecules make up organelles, and so forth. So we're going to start looking at the smallest element there, which is the atom. And this first part of Chapter 2, we're going to focus in on elements. So elements being the comprising all of our matter, which includes living things. We're also going to take a look at how elements have different isotopes, what ions are, and the basics of molecules. Okay, so we're looking at the smallest part of our life's hierarchy, the building blocks. Okay, so this video will cover just the section 2.1 in our Chapter 2 textbook. So keep an eye out for future videos. I will have one covering 2.2, which is focusing on water, and 2.3, which focuses on carbon from our Chapter 2 textbook book there. So by the end of this video, you should be able to define matter and elements. You should be able to describe the interrelationship between protons, neutrons, and electrons. You should be able to compare the ways in which electrons can be donated or shared between atoms. And then you should be able to explain the ways in which naturally occurring elements combine to form molecules, which then a bunch of molecules can form cells, and then cells can form tissue and tissue organs, systems, and finally our organisms. Okay, so this is, we're looking at basically the smallest part of that life's biological hierarchy. So this chapter starts out by basically looking at our life in general. Life in general is made up of matter. Well, what is matter? So matter is anything that takes up and occupies space and has mass to it. So, everything surrounding us is made of matter. And if we take a look at matter, we can divide it into certain elements. So elements are unique forms of matter with specific chemical or physical properties. And elements are the smallest unit of matter that cannot be broken down into smaller subunits by ordinary chemical reactions. So an example of an element would be oxygen, or carbon, or hydrogen, or nitrogen, as you can see in our chart. So table 2.1 from your textbook, we have this chart that kind of shows up the approximate percentage of elements in living organisms. So if we compare us humans to, say, the atmosphere, 65% of the elements in our body are oxygen. Okay, so that's quite a bit compared to the atmosphere, which only has 21% oxygen. If we compare carbon, humans are about 18%, whereas the atmosphere, just a trace amount. If we look at hydrogen, so 10% for humans, whereas the atmosphere is just a trace amount. But then look at nitrogen. So the element nitrogen, about 3% for humans, but 78% is what the atmosphere is made of. So you can see there's, a big difference between the elements within living things like us humans versus the atmosphere. All right, so let's take a closer look at the structure of an atom. So an atom is just the smallest unit of matter that retains all of the elements' chemical properties. So we might, for example, take a look at an oxygen atom. So that would be following the element oxygen, but a specific unit of it, or an atom. So in this picture, we have, in figure 2.2, we have the element helium. So if we're going to look at an atom of helium, we will notice that it's made up of a nucleus, which in this case, the nucleus houses the protons and the neutrons of that particular atom. And then surrounding the nucleus is the electrons, okay? So the reason why we have this kind of setup is because the protons, they have a positive charge to them, whereas the electrons have a negative charge to them. And since positive, negative, those are opposing charges, they cannot be together, okay? So the protons and the neutrons are in the nucleus, the centermost part of the atom, whereas the electrons are surrounding the nucleus, okay? So the outermost region. So here's a table that kind of summarizes what I just talked about. So our atoms are made up of 3 subatomic particles, is what we call them: the protons, the neutrons, and the electrons. So we know that the protons, they're positively charged, whereas the neutrons, they have a neutral charge. They're not positive or negative. And then the electrons have a negative charge. So because the protons have a positive charge and the electrons have a negative charge, the protons are found in the nucleus. The electrons are orbiting outside of it. Also found in the nucleus would be the neutrons, okay? And then one other interesting thing that you might notice about this chart is the mass, okay? So mass, we measure in atomic mass units, or AMU. So one proton will have a mass of 1 AMU, whereas a neutron will also have a mass of 1 AMU. Now look at electrons, 0. So electrons do have mass, but it's such a small amount that we don't even measure it, okay? So protons and neutrons are the only part of the atom that really has mass. The electrons, it's such a minute amount. Okay, so knowing all of this, we're going to take a closer look at an element's atomic number. So an atomic number is determined by the number of protons. When we have something like oxygen, oxygen has 8 protons, so its atomic number is always going to be 8. Carbon has 6 protons, so its atomic number is 6. Now, if we look at a periodic table, which I'll show you in a minute, carbon with its atomic number 6, it will never change the number of protons. So if it has 6 protons, it's never going to have 7 protons. It's never going to have 5 protons. So the atomic number is determined by the number of protons, and that does not change for that element. Okay, so oxygen will always have 8 protons. Hydrogen will always have 1 proton. If it has 2 protons, then it's not hydrogen, it's helium. So the atomic number is determined by the number of protons. We can, however, have a different amount of neutrons in an atom. Okay, so if we have a varying number of neutrons within an element, we end up with something called an isotope. So for example, we might have a carbon atom that has 8 neutrons instead of 6 neutrons. And so that would be a variation of the element. It has 2 more neutrons than it does protons, so it would be considered an isotope. Okay? And we'll get more into that in just a minute. Another thing thing that we can use or calculate is the element's mass number. So the mass number is the number of protons plus the number of neutrons. So if we're talking about the element oxygen, for example, if oxygen has 8 protons and it has 8 neutrons, then its mass number is 16. If carbon has 6 protons and 8 neutrons, then the mass number would be 14. Okay, so mass number is just the number of protons and the mass number of neutrons. Because we can have, within an element, we can have variations of the element where we have different numbers of neutrons for that particular element, we could have a different mass number. And so an atomic mass is calculated mean of the mass number for all of its naturally occurring isotopes. So for example, if we look at chlorine, if we look it up in the periodic table, it says its atomic mass number for chlorine, Cl, is 35.45. Okay, so that means that it's kind of the averaged out of all the naturally occurring isotopes of chlorine. So, for example, chlorine 35, if we have chlorine 35, the mass number would be 35. If we know that chlorine, if we look it up on the periodic scale or a periodic table, its atomic number is 17. So it has 17 protons. So the atomic number never changes. The number of protons never change, but the number of neutrons can. So in chlorine 35, we have 17 protons, and then we also have 18 neutrons. So we have one additional neutron. So that's what makes the mass number 35 for chlorine 35. Another isotope of chlorine is 37. Okay, so chlorine 37 still has 17 protons, but it actually has 20 neutrons. So 3 additional neutrons compared to protons. And so if we add those two numbers up, we get a mass number of 37. So if we take all of chlorine's naturally occurring isotopes and kind of average them out, we get an average atomic mass of 35.47. Okay, so around 35.47. All right, so that's why you see with the periodic table, the mass number and things like that might be a little different than just simply adding equal numbers of protons to neutrons. So here's an example of basically what you will see in a periodic table. So you will see the chemical symbol for the element. You'll see the mass number underneath it, or the atomic mass number, depending on what you're looking at, as well as the atomic number. So for example, in this picture, we see carbon. We see carbon 12. So the mass number is 12. We also see on the right-hand side carbon 13. So this is an isotope of carbon. So it has 13 is its mass number. The atomic number is always the same. Number of protons will always be the same. So here's this question. How many neutrons does carbon 12 and carbon 13 have respectively? Well, if carbon 12 being the mass number, we can calculate the number of neutrons by subtracting the number of protons from the mass number. So mass number is protons plus neutrons. If we know the mass number and we know the atomic number of protons, we can figure out the number of neutrons. So 12 minus 6 protons gives us 6 neutrons. Okay, so we know that the number of neutrons in carbon 12 is 6. If we look at carbon 13, an isotope of carbon, we can see that we have the mass number of 13, and then of course the number of protons stays the same at 6. So 13 minus 6 gives us 7. So there's 7 neutrons in carbon 13. So why do we study isotopes? So we know that isotopes are different forms of an element that have the same number of protons. That never changes for the element, but can have different number of neutrons. So carbon, for example, we have carbon 12. We showed you carbon 13. Carbon 14 is something that is useful in dating very old things like, dead things from the past, fossils. And the reason why we can use isotopes, particularly radioisotopes, is that radioactive isotopes, they emit neutrons and protons and electrons in order to attain a more stable atomic configuration. And we know that it takes quite a long time for one atom to do that. In fact, it takes about, a pretty long time for it to do that. So we can use that information, that idea, to figure out how old something like this mammoth is. Okay, so we can compare the amount of carbon 12 to the amount of carbon 14 that's in it, and it gives us a relatively accurate way of figuring out how old it is. So it's useful in being able to date things like fossils and rocks and things like that. So here's that periodic table I keep mentioning. So with the periodic table, we have basically all of the elements that are displayed. And from this, we can see a lot of information about each particular element. So if we look here at an example of, say, hydrogen, hydrogen's over here, number 1 in our group. So its atomic number is number 1. So I automatically know that it has 1 proton. We see a symbol, so we don't have to write out hydrogen. So the symbol would be H. And then we have the atomic mass. So you can see the atomic mass is 1.008. So that means that, the isotopes of hydrogen, you can see that it averages out to about an atomic mass of 1.008. And then we see the name underneath it spelled out for us. Okay. Another thing that you'll notice as we look at our periodic table is that it is grouped in a weird way. So we have, 1 over here, and then it goes way over here for number 2. Okay, we have 3 over here, 4 over here, and then it jumps to 5. Okay, so we'll talk about why this is in a little bit. Okay, the other thing you'll notice within this chart is based on this information, you can see that over here on the bottom, we can see that we have metal, solid, versus metalloid, liquid versus non-metal gas. Okay, so where are the metals located? So they're kind of more over on the left side of the chart, whereas the gases are located for the most part on the right side of the chart. So we'll talk more about that as well as we get through this unit. Okay, so we'll revisit this, but for now, let's just make sure that we can look at each individual square within our periodic table, be able to identify the chemical symbol for the element, the atomic number, what that means, number of protons, and the atomic mass, what that means, which is the average number of protons plus neutrons within that element. All right, so one thing that we can look at when we look at the periodic table is it gives us an idea of the chemical reactivity of a particular element. And what I mean by that is we can look at, how likely an atom of that particular element is going to want to chemically react with another atom to form a chemical bond. So we learned already in chapter 1 that 2 or more atoms chemically bonded together form a molecule. Now, the reason why we're talking about this now is because it's the electrons that are most likely going to come together first in that molecule. So we need to know where the electrons are within that atom, how many there are, and what's their likely reactivity. So when we're talking about, and an atom, electrons, they tend to fill the orbitals that are closest to the nucleus first, okay? And then the orbitals further away from the nucleus increase in energy, all right? So the outermost electrons in the orbital will determine the atom's electron stability, or energetic stability, I should say, and its tendency to want to react with another atom nearby. So in this case, we see this is hydrogen. Now hydrogen, we know, has one proton, so it's always going to have one proton. If it's a neutral atom, meaning that it has it's electrically neutral, that means that one proton, there's also one electron. Okay, so that kind of cancels out, and it has a electrical neutral charge. So with our one proton in the center of the nucleus, the opposing electron is going to be circulating in orbit surrounding the nucleus. And so this first shell or orbital will be where that one electron is located. Okay, and then just realize that the electron itself is never going to be just in one place. It's going to be constantly moving, but it's going to be moving around in this general area surrounding the nucleus. Okay, and that's if we move outward, it's more energetic, and so this particular electron is going to want to be closer. So when we're talking about our electron orbitals, the innermost shell has a maximum of 2 electrons. So 1n over here can hold a maximum of 2 electrons. That means that if we're talking about an atom that has more than 2 electrons, it'll fill the first shell with its 2, and then move to the second shell. The remaining electrons will be located outward in the second shell. Now, anything above 1n holds 8 electrons. Okay, so 1n, this particular shell has a maximum of 2. The innermost shell has a maximum of 2 electrons. The second electron shell can hold 8. The third 3n can hold 8. So that's the octet rule. So that states that with the exception of the first innermost shell, atoms are more stable when they can have a maximum of 8 electrons filling their shell. Okay. When we're looking at the outermost shell of a particular atom, that is considered its valence shell. So that's where we can see how many electrons it has versus how many electrons it wants to fill that outermost shell. So the valence shell is the outermost electron shell for that particular atom. And it kind of depends on how many electrons it has. So in this case, hydrogen has 1 electron. So its outermost shell is 1n, and its valence shell is, this first one. And in this case, it wants 2 to fill its outermost shell. Okay, so that would be its most stable. All right. So here's some examples of some other Bohr models of different elements. So we already talked about hydrogen. Filling its outermost shell, it needs a maximum of 2, but only has 1. If we look at helium over here, helium has 2 electrons in its stable form, which is the usual form. So it's actually very stable because it's already filled its outermost shell. So helium, for example, is less likely going to want to react with another atom to form a molecule because it's already happy. It's in its stable form. It has its outermost shell filled. If we look at lithium, lithium has 3 protons, so that means that if it's a neutral charge, it has 3 electrons. So the first 2 electrons will fill the first shell. Remember, the innermost shell has a maximum of 2. And then that extra electron will move into the second shell. Okay, so that has just 1 electron outside in the 2n. Okay. If we take a look at something like carbon, carbon has 6 for its atomic number. So electrically neutral carbon atom has 6 protons, 6 electrons. So we can see that the first 2 electrons fill the first shell, and then the other 4 electrons are kind of distributed in the second shell. If we look at something like neon, neon has it has 10 protons, and so if being electrically neutral, it would also have 10 electrons. And so we can see 2 of those 10 electrons will fill the first shell, and then the second shell is also completely filled. Its valence shell is completely filled with 8. And so this is a very stable atom. Okay. If we have more than 10 electrons, then we'll start filling the third shell. So the third shell can also have a maximum of 8. So we fill the first shell first, so the innermost shell first, that's 2. The second shell can have a maximum of 8, and the third shell can also have a maximum of 8. So if we take a look at this kind of this figure here from your textbook, let's see if we can understand or figure out these questions here. So it says, looking at this figure, how many electrons do elements in group 1 need to lose in order to achieve a stable electron configuration? So remember, a stable electron configuration is filling its outermost shell. So we're looking at group 1, and notice group 1 has 1 electron in its outermost shell. So most likely it wants to lose that electron. Okay, so if it loses that electron, then it drops down to a different valence shell, okay, which is already filled. So it will need to lose 1 electron in order to be a little bit more stable. Okay. This question, how many electrons do elements in group 14 need to gain in order to achieve that stable configuration? So let's look at group 14, kind of hidden there. So here we have a carbon atom, and in its valence shell it has 4 electrons. So how many does it need to gain in order to fill its outermost shell? Well, it needs 4 more, right? So it needs to have 8 total to be stable. Silicon over here, in its outermost valence shell, it also has 4. So it would need to gain 4 in order for it to reach its most stable form. Okay. What about group 17? So here's 17. We have fluorine, we have chlorine. Let's look at their valence shells. So in this case, we have 1, 2, 3, 4, 5, 6, 7 electrons in its valence shell. So how many electrons does it need to fill it? Just 1. Okay, it wants a maximum of 8 to fill its outermost shell, so it just needs 1. It just needs to gain 1. Same with chlorine. It has 7 in its outermost shell. Just needs 1 more to achieve the stable configuration. Okay. So if we take a look at our periodic table again, we can see those groups a little bit more clearly. So group number 1, we know, always has just 1 electron in its outermost shell. Group number 2, they're going to have 2 electrons in their outermost shell. Okay. If we look over here, we're going to ignore these guys. If we look over here, fluorine, it's going to have 7 electrons in its outermost shell. Group number 16, okay, that will have 6 electrons in its outermost shell. So based on that information, it can kind of give us an idea of which of these atoms are most likely going to want to gain electrons and which will most likely want to lose electrons in order to fill their outermost shells. So for example, group number 1, since they have 1 electron in their outermost shell, they most likely want to get rid of that 1 electron in their outermost shell and drop down to a more stable form. And because they want to get rid of one, they would end up having a difference in the number of protons and the number of electrons. So they might become charged, and a charged atom is called an ion. Okay? So for example, lithium, we saw in our previous example, let me just go back. Lithium is going to want to get rid of that extra electron. So if it gets rid of that extra electron and drop down to a more stable form, then it only has 2 electrons. If it got rid of that one, it would only have 2 electrons. But it has, its atomic number is 3, so that means it has 3 protons. So if it has 3 protons and only 2 electrons, it's going to have 1 extra proton or 1 extra positive charge. So it will become an ion. Okay, so ions, they are no longer neutral. Group 17 is most likely going to want to gain an extra electron. So if we look at, for example, fluorine and chlorine from our previous slide, fluorine and chlorine, they just need 1 electron in order to fill their outermost shell. So if they gained that electron, they now have their outermost shell filled. And if they gain that electron, so if fluorine, its atomic number is 9, has 9 protons, but if it gained an extra electron, now it has 10 electrons. So it will be a negatively charged ion. Now over here in group 18, these elements over here, they're considered, sorry, not these guys down here, but these are considered noble gases or inert, and that's because they filled their outermost shells. So if we go back to the previous slide, neon, for example, is naturally going to fill its outermost shell. So it's not going to want to, gain or lose electrons because it's already filled. It's a happy, stable atom. Okay, same with argon. Argon has its outermost shell filled, so it's very stable. So it's not going to want to react with a nearby atom to form a molecule. Same with helium over here. So we call those particular elements that have filled their outermost shells naturally in their stable form, those are inert or noble gases. Okay. So this gives us a little bit more idea when reading our periodic table. We can use this to kind of predict which ones are most likely going to want to gain or lose electrons, which ones are not going to want to react at all, and so forth. Okay. Now, when we're talking about a Bohr model, okay, going back to our previous slide here, a Bohr model is just kind of showing where the electrons, they're going to be within relative to the outermost shell. Okay, but electrons are constantly moving. They're not just going to be stabilized like here's this electron sitting there forever. No, it's constantly moving around. So we can kind of predict where electrons are most likely found by looking at the electron orbitals. So an electron orbital is the area where an electron is most likely found. So within these orbitals, we have these subshells. So the first subshell would be an S subshell. So an S subshell is spherical in shape. So if we take a look over here on this diagram, this blue area right here is our first 1n S subshell. Okay, so this is where most likely the electrons for 1n will be. Okay, so if you remember going back to our Bohr model, I'm just going to keep going back and forth. 1n is this first shell. So that electron, it's not always going to be just here. It could be here, 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 it could be here. It's just floating around in kind of this sphere within that shell. Okay, so this is the 1n S subshell. Now that principal shell One N can hold a maximum of 2 electrons, okay? So it only has a single s orbital. So those 2 electrons are just going to be hanging out in this area, okay? Moving up, if we're moving into the second principal shell, 2N, remember 2N can hold a maximum of 8 electrons. And so the first 2 electrons will be in what we call the 2NS shell, okay? So an S shell being spherical, so this would be this kind of reddish sphere, okay? So those first 2 electrons will be kind of hanging out in those areas. Okay. Then we have what's called a P subshell. So the P subshell is these 3 dumbbell-shaped orbitals. Okay, so here's a dumbbell-shaped orbital, here's a dumbbell-shaped orbital, and here's a dumbbell-shaped orbital. So the electrons will, basically be found in these dumbbell shape. So if we're filling the 2N shell completely, 2 of the electrons will be kind of in this spherical area, okay? 2 of the electrons will be filling one of the p orbitals. 2 electrons will be hanging out in another p orbital. 2 electrons will be hanging out in another p orbital. So we can have a maximum of 8 electrons in the principal 2N shell. Okay. If we're going to go beyond that, if we have more electrons, we might get into more complex subshells. So D and F, they have more complex shapes. And a D orbital or D subshell can hold, D can hold a maximum of 5. Subshell F can hold a maximum of 7 orbitals surrounding the nucleus there. So if we're focusing in on something like 3N, remember our 3N, if we go back, here's 3N is filling. So 3N, we have a 1N, a 2N, and a 3N, okay? Now if we're looking at that in our diagram, okay, so a 3N can have an S subshell, a P subshell, and a D subshell. And that will allow it to hold a maximum of 18 electrons. Whereas our principal 4N shell could have an S, a P, D, F orbitals, and they can hold a maximum of 32. So let's take a closer look at this in a little video that kind of describes it. Okay, so in this video we're going to see kind of those translucent orbitals of where the electrons might hang out. So if we have the 1s subshell, we're going to see how we have 2 electrons. Here's 2s coming in, so here's another 2 electrons might be hanging around in that general area. Here's our going into our 2p subshells, so we can have 3 of these dumbbell shapes. So there's the first one, 2px, and then here comes 2py, and then we'll see 2pz coming in. So that's just another, where those electrons might be. Okay. Moving in, we'll have 3s. Okay, so in 3s, that's the spherical shape. Another 2 electrons might be hanging around in that area. Here's 3px, so here's the dumbbell shape. We'll see 3py come in, another dumbbell shape. And then, can you guess what the next one is? 3pz, the third and final p dumbbell shape. Okay. Going up, we have 4s, so this is the next kind of area that the electrons will inhabit. And in this case, we have a D subshell. So D subshells, they're more complex in shape, so they're not going to be just kind of that standard spherical or dumbbell shape that we saw with the S and the P. Okay, so you can kind of see how weirdly shaped, more complex they are. So So once that fills in, that's pretty complex. We're not going to go on to the f orbital in this example. So we're just showing the different areas, complexity of the d. So here you can just kind of see all of the possibilities of the d. Okay, the d orbitals. All right. So in a basic biology class, we don't normally just focus in on the s, the p, the f, d orbitals of those electrons. But this just kind of gave you a little bit of an idea of that. So what we're going to do next is we're going to see what happens when a particular atom wants to get rid of or gain an extra electron to fill its outermost shell. So we end up with a chemical reaction where we have two atoms or more than two atoms that are going to want to fill their outermost shells by forming a chemical bond with each other. So chemical bonds, where we have these atoms, they can achieve their outermost shells by gaining, losing, or sharing electrons. And of course, if we have two or more atoms that are chemically bonded together, we form a molecule. So here's an example. We have hydrogen. It has one valence electron. It wants a second electron in order to fill its outermost shell. Oxygen here has 6 valence electrons, so it wants 2 more electrons to fill its outermost shell. So they will maybe share those electrons to form a chemical bond between them. And now we have a water molecule. So whenever we have 2 or more atoms bonded together, they're formed through a chemical reaction. And so when we want to describe that chemical reaction, we might use it in some sort of chemical equation. So here is an example of a chemical equation. And in this case, anything to the left of the arrow are considered the reactants. So they're the beginning of the chemical reaction. Anything to the right of the arrow are the products, so the substances at the end of the reaction. So in this case, the start of the chemical reaction, we had 2 hydrogen atoms, so that 2 in front of H means that there's 2 of these hydrogen atoms and 1 oxygen atom. So this is the beginning of the reaction, just like in the previous slide. Go back. There we go. In our previous slide, we had 2 hydrogen atoms and 1 oxygen atom. So these are the reactants. And then once they've chemically reacted together, they form H2O. So that is the product. And we know that they're chemically bonded together because there's no space between, like we have in this picture here, or this figure. So they're chemically bonded together, 2 hydrogens and 1 oxygen together to form a molecule. Now, if we have equal numbers of atoms on the reactant side versus the product side, we consider that a balanced chemical equation. So here is an example of that. Hydrogen peroxide, we have basically 2 of these molecules. So we have H2, so there's 2 times 2, so we have a total of 4 hydrogen atoms in these 2 hydrogen peroxide molecules, so 4 total. On this side of the equation, we have H2 times 2, so 2 times 2 would be 4 hydrogen atoms total. So we have equal number of hydrogen atoms on both sides of the equation. If we look at the amount of oxygen, we have O2 times 2, so 2 times 2 equals 4, so we have 4 oxygen atoms. Over here, we have 2 oxygen atoms forming this molecule, plus we have 2 more. So 2 times 1 would be 2. So 2 plus 2 equals 4. We have 4 total oxygen atoms. So this is balanced because we have equal number hydrogen on both sides of the equation, equal number oxygen on both sides of the equation. Okay. Now, we keep talking about molecules. So molecules are when we have 2 atoms that are chemically bound. A compound is a little different in that we can have 2 atoms where they're not the same elements. Okay, so it contains atoms of more than one type of element. So oxygen right here, for example, is a molecule of oxygen, but it's not a compound because it doesn't have more than one element. Right? Water would be considered a compound because it's a molecule bound together, but it has 2 different types of elements there. Now within our chemical reactions, some of our chemical reactions are irreversible, some of them are reversible. So an irreversible chemical reaction basically means that it proceeds in just one direction until all the reactants are expended. Okay, so for example, here we have 2 oxygen atoms. They're going to form an oxygen molecule, and it's just going in one direction. A reversible reaction means that it can go in either direction. So we can have the reactants and the products forming the products, and then the products can also break down and form reactants again. So they can go in either direction, and they might do this continuously until they reach a state of equilibrium. So here's an example of a reversible reaction. So we have HCO3 minus, so this is actually called bicarbonate. And this bicarbonate, and then we have H plus, so H plus, this is a hydronium ion. Because it's an ion, it's got a positive charge. This is an ion because it has a negative charge. So these 2 can react together to form something called carbonic acid. So H2CO3 is called carbonic acid. Now that carbonic acid could then react to form bicarbonate and hydronium ions again. Okay, so it's reversible, can go either way. Down here you can see how we can have an even more complex reversible equation where we have the bicarbonate ion and the hydronium ion forming carbonic acid. That carbonic acid could then break back down into bicarbonate and hydronium, or it could break down into carbon dioxide and water. So we can see that, this is a little bit more complex. All right. Now, speaking of ions, we just saw how we have an hydronium ion, H+. That is a positive ion, so it has an extra, compared to the protons and electrons, there's more proton than electron. So it's positively charged, and they're formed by losing electrons. So we consider those type of ions cation ions. So cation ions are positive ions. An anion is like our bicarbonate in the previous slide. So it has a negative charge because it has gained extra electrons. So those negative ions are called anions. Now when we have a one atom that is losing electrons and another atom gaining that electron, it is called an electron transfer. So we're simply transferring one electron to another. And this is, when this happens between 2 atoms, it forms what's called an ionic bond. So an ionic bond is between ions of opposite charges. So here's our example. We have our sodium atom, and if you recall, sodium is in group 1 of our periodic table. So it has 1 electron in its outermost shell. So it wants to lose that electron in order to drop down to a more stable configuration. Chlorine is in group 17 of our periodic table, so it actually wants to gain an extra electron to fill its outermost shell. Since it has 7 valence electrons, it wants one more. And because of that, we're going to see this electron transfer. So most likely that sodium is going to give up that electron to chlorine. So we can see that electron transfer. And now they've dropped down, or they filled their outermost shells, and so they're more stable. And so these two together have formed an ionic bond. Now the ionic bond is a relatively weak bond compared to our next chemical bond called a covalent bond. So covalent bonds, these are going to be the strongest type of chemical bonds, because instead of gaining or losing electrons, the atoms in the molecule are going to share the electrons. And since they're sharing the electrons, they don't want to lose that electron, so they're going to hold tight together. And so here's an example of a covalent bond. We have a water molecule, for example, H2O. So we have 2 hydrogen ion atoms, and those atoms, they have 1 valence electron, so they want another one to fill their outermost shell. Oxygen has 6 electrons, so it wants 6 valence electrons, so it wants 2 more to fill its outermost shell. And so in this case, they're going to be sharing those electrons. And with them sharing the electrons, they're filling their outermost shells. But there's always a chance they can lose it, so they want to hold tight together so that they don't lose the electron that is filling their outermost shell. So covalent bonds are very strong. So we're going to watch a video that kind of shows the difference between ionic and covalent bonding.
Ionic bonding occurs between 2 atoms when one of the atoms has sufficient strength of attraction to remove an electron from the other atom. A sodium atom has 1 valence electron, with a stable energy level below containing 8 electrons. A chlorine atom has 7 valence electrons. If the atoms collide with sufficient energy, the chlorine atom will remove the electron from the sodium. The sodium atom loses its only valence electron and becomes a positively charged sodium ion. The energy level below now provides sodium with its stable octet. The extra electron completes a stable octet for chlorine, which becomes a negatively charged chloride ion. Covalent bonding occurs when neither atom has sufficient strength to completely remove the other atom's electrons. The atoms share electrons, and both atoms achieve a stable outer energy level. A hydrogen atom with 1 valence electron needs 1 additional electron to complete the first energy level. An oxygen atom has 6 valence electrons and needs 2 additional electrons to complete the second energy level. As the oxygen and hydrogen atoms collide, covalent bonding is accomplished by the sharing of electrons. By sharing an electron pair with the oxygen, the hydrogen completes the noble gas configuration of helium. By sharing with the hydrogen atom, the oxygen atom now has 7 electrons in its energy level, still 1 short of the stable octet condition. A stable octet for oxygen can be completed by sharing an electron with another hydrogen atom.
All right. Now, within our covalent bonding, we know that we're sharing those electrons. But sometimes, if you notice from that video, it almost seemed like there was an unequal sharing. So when you're watching those electrons moving around, sometimes the hydrogen, there's no electrons on one side of it. And so we can end up with this kind of unequal sharing where it seems like the oxygen's hogging the electrons. And so in that case, we call it a polar covalent bond. So polar covalent bond means that there's an unequal sharing of electrons, where one atom is kind of you see the electrons surrounding that atom more often than you see the other one. And in this configuration, we end up with, because we see that the electrons are more orbiting one atom versus the other, the outside of those atoms, they can start getting a negative or a positive charge to them, or a partially negative, partially positive. It's not always going to be positive for hydrogen, for example, because occasionally you will see that electron orbiting its nucleus. You won't always see a negative charge on an oxygen atom in this form, because sometimes it will have lost that one electron, and that's circling the hydrogen at that point, making it more stable. Or more neutral. So you'll see these symbols. This means partially negative, this means partially positive. So because of that unequal sharing of electrons, the oxygen side of this molecule will tend to have be a little bit more partially negative. The hydrogen side of this molecule will be more partially positive. So we call that a polar covalent bond. Here's another example of a polar covalent bond. We have a water molecule. So we have two hydrogen atoms and an oxygen atom sharing electrons with each other. And because it's an unequal sharing, we'll see the partially negative end of the oxygen end of the water molecule being partially negative, and the hydrogen ends of this water molecule being partially positive. So that means it's polar. A non-polar covalent bond means that they're equally sharing. Okay, so there's an equal chance that the shared electron will be orbiting the carbon versus the hydrogen at an equal rate in this case. And so they're equally sharing it. So there's no partial negative, partial positive charge. Here's an example where we have methane. Methane is C4, so there's, or CH4, excuse me. So there's 4 hydrogens covalently bonded to the carbon, and they're equally sharing those electrons, so it's a non-polar covalent bond. Sometimes we can see a nonpolar with carbon dioxide as well. So in carbon dioxide, you can see the oxygen on either side of the carbon, where they're kind of equally sharing the electrons in a more nonpolar shape there. Okay. Now, we know that the covalent bonds are the strongest bonds because they don't want to gain or lose that one electron or one or more electrons that are in their outermost shell. Ionic bonds tend to be weaker bonds because there's that likelihood that they do want to fill their outermost shell by gaining or losing. Hydrogen bonds and van der Waals interactions are also considered weak interactions or weak bonds. So they will, form and break all the time. So a hydrogen bond is a weak interaction between a hydrogen's partially positive end from one molecule to a partially negative charge of another nearby molecule. Okay, so with a hydrogen bond, we don't just have hydrogens floating around. So they're usually already bonded to something, such as oxygen. But in that bond, because it's a polar covalent bond, they might have this unequal sharing of electrons. So the hydrogen end of that molecule is going to be partially positive. And because it's partially positive, it becomes a situation where the hydrogen, might want to, also bond with something else that's going to give it more of a charge there. And so because of that, we end up with these hydrogen bonds. Okay. So water molecules, we'll talk more about this in the next video on water specifically. Water molecules, when we have 2 water molecules, they will form hydrogen bonds with each other. Whereas the water molecule itself is made up of a polar covalent bond. Okay, so our final chemical reaction we're going to talk about, our chemical bond, is a van der Waal interaction. So van der Waal interactions are very weak interactions between molecules due to some sort of like slight fluctuation or change in their electron densities. And so because of that, they're going to not always be, the electrons are not always going to be symmetrical around the atom. And so when we have two molecules that are very close together, you might see a slight attraction to them, a weak interaction between them. And so they might form like that temporary bond. Okay, so let's go ahead and finish off this video with some review questions. So here's our first review question. We have, if xenon has an atomic number of 54, so wow, that's, you know, pretty deep in our periodic table, so we've been kind of dealing with the smaller numbers. So we have an atomic number of 54 and a mass number of 108. How many neutrons does it have? Well, how do we figure that out? Now the atomic number is also the number of what? The number of protons in that element. So if xenon has an atomic number of 54, we know it has 54 protons. It will always have 54 protons. It'll never have 55 or 53 protons. It will always have 54. So we know the number of protons. The mass number is 108. Well, how do you calculate a mass number? It's the number of protons plus the number of neutrons. So in order to figure that out, the number of neutrons, well, we simply have to take the mass number and subtract the number of protons from it, and that'll give us the number of neutrons. So what's 108 minus 54? 54. So this particular atom has 54 protons, 54 neutrons to make the mass number 108. Okay. Here's another question. Atoms that vary in the number of neutrons found in their nuclei are called, well, are they ions, are they neutrons, are they neutral atoms, or are they isotopes? So if we have varying number of neutrons, then they're called isotopes. Okay. Remember, atoms that have, gained or lost an electron would be an ion. Okay, but an isotope would be varying number of neutrons. Here's another question. Potassium has an atomic number of 19. What is its electron configuration? Now notice it doesn't say it's an ion, so we're going to assume equal number of protons to neutrons, or electrons, excuse me. So if the atomic number is 19, that means there's 19 protons. And since this doesn't say that it's an ion, then that means it has 19 electrons as well. So we got to figure out its electron configuration. So the first shell can have how many electrons? It can have a maximum of 2. So of the 19, 2 will be in the first shell. The second shell has a maximum of how many electrons? It can hold 8 electrons. So 2n equals 8, so that octet rule. So we have our first shell has 2, the second shell has 8, so now we're at 10 electrons. Move into the third shell. This third shell also can hold 8. So we have 2, shell number 1n has 2, the second shell has 8, so that's 10, plus the third shell has 8, that's 18. So we're going to move into the fourth shell. So the fourth shell can have a maximum of 8, but we've already accounted for 18 electrons, so only one's going to be there. So based on that information, let's see which answer is correct. So shells 1 and 2 are filled, that's correct. Shell 3 has 9 electrons. Well, it can't have 9 electrons because the octet rule says it can have maximum of 8, so that one's wrong. Shells 1, 2, and 3 are full, that's true. But shell 4 has 3 electrons? No, because we have a maximum of 19. Shell number 1 can have 2, shell number 2 can have 8, shell number 3 can have 8. So that's 18 of our 19, we only need 1 in the 4th shell. So it must be this one. Shells 1 and 2 and 3 are full, so that's true. And then shell 4 has 1 electron. So we've maximized the first 3 shells, and then that leftover electron's hanging out in the 4th shell. And then we have this question: which type of bond represents a weak chemical bond? So we talked about ionic bonds, covalent bonds, hydrogen bonds, and van der Waals bonds. So which one of these, or interactions, so which one of these is going to be within our, which one of these is the strongest? Would be the covalent bond. So we can't choose covalent bond, nonpolar covalent bond, that's a covalent bond. So these two are strong. So we have ionic bonds, we have van der Waals interactions, and we have hydrogen bonds. So which one represents the weak one here? Well, atomic bomb, that doesn't make sense. We didn't discuss anything like that, so that one's just a non-answer. So it must be hydrogen bonds. Those are the weak bonds here of the 4 choices. All right, so we have completed the first part of chapter 2. So now we have an idea of what atoms are, isotopes, ions, and then we've talked about chemical bonding with ionic bonds, covalent bonds, and hydrogen bonds, and even talked a little bit about those van der Waals interactions. So the next part of chapter 2 gets into water. So if you are going to continue on, the next video will cover that section 2.2 on water. And of course, as always, go ahead and click the subscribe button to make sure that you don't miss any of those new videos that get posted. Okay. For those of you that wrote down those learning objectives, make sure that you try to answer those on your own and see if you remember. So those learning objectives covered this first section. All right, so I'm going to move on to that next video.